Very good morning, students. Welcome to the science session. Today we are going to continue with the lesson Unit 5 Acoustics. Now, in the last session, we have learned what is sound wave, the characteristics of the sound waves based on the frequency, difference between the sound waves and the light waves, and we have also seen the factors affecting the velocity of the sound. And what is reflection of the sound, the laws of reflection of the sound, and what is the reflection at the boundary of the denser. A very good morning, students. Welcome to the science session. Today we are going to continue with the lesson Unit 5 Acoustics. Now, in the last session we have learned what a sound wave, the characteristics of the sound waves based on the frequency, difference between the sound waves and the light waves, and we have also seen the factors affecting the velocity of the sound. And what is reflection of the sound, the laws of reflection of the sound, and what is the reflection at the boundary of the denser medium, reflection at the boundary of the rarer medium, and reflection of sound in the plane and the curved surface. So let's continue with this lesson. Today we are going to see about what are echoes. What is the application of the echo? What is Doppler effect? What do you mean by Doppler effect? And we are going to derive the formula. It's actually the formula of the apparent force due to the Doppler effect, and we are going to use this formula in the numerical problems, and so we'll be dealing with few numerical problems. Let's go into the session, children. Now, in the last session, we have learnt about the law of reflection, isn't it? Similar to that of the light waves, the incident ray, when it meets an obstacle, it gets reflected and you get the reflected sound. And we also said that the angle of incident is equal to the angle of reflection, and the incident wave, the reflected wave, and the normal all lie in the same plane, right? So this is what about the law of reflection. Now, if this is the reflection, now what about echo? What is an echo? Now, an echo is the sound produced due to the reflection of the original sound from various rigid surfaces like walls, ceilings, mountains, or the any rigid surfaces you can say, and it reaches our ears in the form of a sound, right? So a repeated sound again and again. So what is an echo? Echo is the repetition of the same sound again and again. So the reflection of the original sound. For example, if you shout or clap near a mountain or the wall near a rigid wall surfaces, right? Now what will happen? The reflected rays moves, it meets an obstacle, and again it gets reflected way, right? So the sound which is heard again and again is called as an echo, and this is due to the reflection of the sound. For example, if you are in a very small room, right? So one do not experience any echo in a small room. So what does it mean? What are the basic conditions that is required for an echo? Now, for example, take this case. Now consider that you are clapping a wall in the open space where you have a rigid wall in front of you. So when you clap, you hear your sound again and again. Now, why it happens? Now, this is because the incident wave travel in all direction. Now, when it travels in all direction, as it meets the obstacle, it gets reflected back, right? So when it is reflecting, right, when the incident rays, when many incident rays are diverted in many directions, and when it meets an obstacle, it gets reflected, and these reflected rays here reaches our eye, and you are getting the repeated sound of the original sound. Now, for example, if I'm clapping my hands, the original sound is clapping of hands, isn't it? Or if I say hello in front of a mountain, I get an repeated sound, isn't it? So my original voice hello is the original sound, and the repetition I hear is the echo. So this is how it reaches our ears. Just now we said that when I am in a small room, right? So one will not experience any sound in a small room. So it doesn't mean that the sound is not reflected in the small room, but it means that the small room do not satisfy the basic condition of hearing an echo. Then what is the condition for hearing an echo? So the basic condition for hearing an echo is that there are two basic conditions. The first one is that the minimum time gap between the original sound and echo must be 0.1 second, right? The gap, there is a time gap, there will be a time gap between the original sound and an echo, because the original sound has to reach the obstacle and it has to reflect back, isn't it? So there will be a time gap, but this time gap should not be more than 0.1 second. So the time gap between the original sound and the reflected sound should not be more than, or the minimum sound that is required between the original sound and an echo should be 0.1 second. So this is one of the condition. The next condition for an echo is temperature. The temperature should be 22 degrees Celsius. If the temperature is 22 degrees Celsius, the echo can reach our ears. Now, what is the third condition? The third condition is that the distance between the source and the obstacle should be 17.2 meters, or you can say the minimum distance required to hear an echo is 17.2 meters. The distance between the source of the sound and the reflecting surface, right? So these are the conditions. So in your textbook only two conditions is mentioned. The first one is that the minimum distance between the source and the reflecting surface should be 17.2 meters. And what is the next condition? The minimum time gap between the original sound and an echo must be 0.1 second. So the time gap should be 0.1 second and the distance should be 17.2 meters. So these are the two conditions that is required for hearing an echo. Now let's see the application of echo. Now here you can see here a ship which sends the sound waves and it is reflected back to the ship. Now this application is nothing but the sonar. Now here the application of the echo is used to identify or to detect the distance of the seabed or any object that is present in the ocean. Now there are many applications of the echo. The first one is this one, that is sonar. The next is the principle of the echo is also used in the ultrasonography. So this creates an real-time images in the developing embryos or the fetus in the mother's uterus, you can say. And this is also a very safe tool because it do not produce any harmful radiations. And echo is also used to determine the velocity of the sound waves in any medium. In any medium, the velocity of the sound can be calculated. Sonar is also one of the application. You can see in the picture here where the reflected wave reaches back to the ship to identify the distance where exactly the object is present under the sea. The next one is the some animals. If you see, some animals communicate to one another over a long distance, or you can say it can locate the object by sending some sound signals, and it also receives the echo back from the target. Now here you can see the bat targeting the prey. Now it sends some signals, and depending upon the signal that receives by the obstacle or the prey, it detects the object, how far is the prey located. Now this is about the applications of echo. Now I said that the echo can be used to calculate the speed of the sound in any medium, isn't it? Now since the incident or the original sound travels, meets the obstacle and again reflected back, so the distance covered by the sound is 2 times, isn't it? So the sound impulse transmitted from the source has to travel the obstacle, again it has to come back to the source, isn't it? So the distance is taken as 2d and the time taken for this is taken as t. So the speed of the sound is nothing but the distance traveled by time taken, and here we said that the distance is taken as 2t because the sound has to start from the source, meet the obstacle here, again it has to meet the source again, isn't it? So now here this is D and this is 1D, so this should be added, so you will get 2D, right? So this is the speed of the sound in a medium. Now the next one is the Doppler effect. Now what is Doppler effect? To understand Doppler effect, let us see an example. Now here you can see an ambulance making sound, and this ambulance is moving with respect to a person standing here, right? So a person is standing here and the ambulance is in motion with the sound. Since the ambulance is in motion with respect to the stationary observer, right? Now here this is the source because it produces the sound, and he is the observer, so he is a listener. So the source is indicated by the letter S and the listener is indicated by L, or it can also be taken as an observer, right? So when the source is moving with respect to the object, now if it is moving in this direction, right, and the listener is here, right, now the frequency of the sound that is heard by the listener changes with respect to the motion of the source. Now for example, now if the source is here, right, the frequency heard by the listener will be more. Now if the ambulance moves away from the listener to a certain distance, the frequency heard by the listener will be less compared to the position here that we have set before. So there is an apparent change in the frequency that is heard by the listener, isn't it? So this apparent change in the frequency with respect to the source is called as the Doppler effect, right? So here you can see the definition. So the apparent change in the frequency of the sound when the source of the sound and the observer and the medium are in relative motion. So any one can be in motion, or both the source and the listener can be in motion, right? So if the source and the listener are in relative motion, right, there is a change in the frequency that is heard by the listener or the observer, and this apparent change in the frequency is called as the Doppler effect. Now we said that the listener and the observer are in relative motion, isn't it? So this relative motion can have various possibilities. The first one is that the listener move towards or away from the stationary source. Now for example, source is here, right? So this is at stationary. Now when I make a round, it means that it is at rest or at stationary position, right? So this is at stationary position, and the listener is moving towards the stationary source or away from the stationary source. This is towards the stationary source and this is away from the stationary source, isn't it? So when the listener is moving towards the stationary source or away from the stationary source, so this is one of the relative motion possibilities. The next one is that the source moves towards or away from the stationary listener. Now here the listener is at rest, right, and the source is moving towards the listener or away from the listener. This is towards and this is away. So the source is moving towards the listener or away from the listener. So this is again one of the possibility. Now let us consider this possibility, right? So where the source and the listener is moving towards each other. Now if V is the velocity of the sound and Vs is the velocity of the source and Vl is the velocity of the listener and N is the frequency of the source and N dash is the apparent frequency or the frequency of the sound that is heard by the listener, right? Now how will you calculate the apparent frequency? Apparent frequency is calculated using this formula where N dash is the apparent frequency. This is given by N dash is equal to V plus VL divided by V minus VL into N, where V is the velocity of the sound and VL is the velocity of the listener, Vs is the velocity of the source, V is the velocity of the sound, and N is the frequency of the source, right? So N dash is the apparent frequency, that is the change in the frequency we said, isn't it? So this can be calculated using this formula. Now using this formula we are going to calculate the formula for the various possibilities. Now we have a tabular column for this. Now all these formulas are very important because using this you have the numerical problems. Now here you can see in the tabular column, so this is the formula that we have dealt now when the source and the listener are moving towards one another. Now we'll go to the second cases. Now here both the source are moving, but they are moving away from one another. Now here the source and the listener are moving away from one another. In the first case, source and the listener are moving towards one another. Now in the second case, the source and the listener are moving away from one another. Now with respect to this formula, we can derive this formula. Now if the direction is towards one another, so this is the formula. So the source is moving towards the listener, isn't it? So in the numerator you will have the positive sign and in the denominator you will have the negative sign. Now since the source and the listener are moving away from one another, so you have to write the reciprocal of these two symbols. So here you will get the negative sign and here you will get the positive sign. But the formula is V minus VL divided by V plus Vs into the frequency of the sound. So this is how you can relate one formula with the other and you can memorize it or recall it. Now let us see the third case. Here the source and the listener are moving, but the source is following the listener. Now here you can compare this with the second case. Now here if you compare it, what is the direction of the source and the listener? Now the direction has changed, isn't it? Right? So here you will, in the denominator you will say change the sign. Now here you have the positive sign, here you can make it as a negative sign. Now here, since the listener is in the same direction, here in the numerator you can have the same formula, right? So n dash is equal to, or this apparent frequency is equal to V minus VL divided by V minus Vs into the frequency of the sound of the source. So this is the formula and this is the one of the possibility. Here now let us consider the fourth possibility. Now both the source and the listener are in motion, but the listener follows the source. So the source is moving in one direction and the listener is following the source, right? Now in this case, both the listener and the source are in the opposite to the direction that we saw in the third case, isn't it? So here in the third case, both the numerator and the denominator had negative sign, isn't it? Now here it will become a positive sign because it is opposite to that in case 3, right? Now next see the fifth possibility, that is source is at rest, right? Now when I said that it is, when it is written in a circle, it is at rest, right? So the source is at rest and the listener is moving towards the source. Now if the listener is moving towards the source, now here the source is at rest. Now here Vs will become 0, isn't it? The velocity of the source becomes 0, isn't it? So here you will have, now see the direction here. Now it is same as that of the case 4, isn't it? So here you will have a positive sign in the numerator and in the denominator you have only the velocity of the sound because the velocity of the source is 0. Now let's see case 6. Now here the source is at rest and the listener is moving away from the source. Now the listener is in the opposite direction, right? Now we saw in the fifth case, that is the listener is moving towards the source. Now here the listener is in the opposite direction. Now here in the numerator you will have a negative sign. In the previous case it was positive, isn't it? So the denominator will be the same because the source is at rest, right? So Vs will be equal to 0. So in the denominator you will have only the velocity of the sound, right? Now look into the seventh case. Now here the listener is at rest, right? And the source is moving towards the listener. So what will be the numerator? Numerator will have only V because VL in this case is equal to 0, right? And now what is the source? The source is moving in towards the listener, isn't it? So it will have a negative sign. Now here look into the 8th case, children. Here the listener is at rest and the source is moving away from the listener. So since it is moving away from the listener, it is opposite to that. You compare these two. Now the direction is opposite, isn't it? So in the denominator there will be a change in the sign. So here it is negative and here it will become positive. While in the numerator it will be the same, because here also the listener is at rest, and even in the case 8 the listener is at rest. So this is how you have to remember the formula with respect to one other case, right? So these formulas are very, very important because we have numerical problems using these formulas. Here we are going to see the conditions for no Doppler effect. When there will be no Doppler effect, in which situations, in which circumstances there will be no Doppler effect. Now there are 4 conditions in which no Doppler effect can be seen, right? When the listener and the source both are at rest. Now, so the listener is also at rest and the source is also at rest. When both are at rest, then there will be no Doppler effect. Is that clear? So there will be no change in the apparent frequency. So this is the first condition. The next one is that the source and the listener move in such a way that the distance between them remains the constant. Now consider the source and the listener are moving in any direction. Either it can be in the same direction, or it can be in the opposite direction, or one following the other, right? Now, even if it is moving in the same direction or in the opposite direction, the distance between the source and the listener should be constant, whether it is moving towards one another or away from one another, or one follows the other, right? So if the distance is maintained between the source and the listener, there will be no Doppler effect. Next is that when the source and the listener are moving mutually perpendicular to one another. Now, for example, if the source is moving towards the north direction, right, and the listener is moving, now these two are perpendicular, right? So when they are moving in a perpendicular direction, right, when the source is moving this direction and when the listener is in the perpendicular direction, then there will be no Doppler effect. The next one is that if the source is situated at the center of the circle and along which the listener is moving in a circle. Now, for example, see, the source is at the center of a circle and the listener L is moving along the circle, right, as in the circumference of the circle, where the source is at the center of the circle. Now, if this is the case, then there will be no Doppler effect. So these 4 conditions are necessary for a no Doppler effect. Now, if you see the applications of the Doppler effect, it is used to measure the speed of the automobile, right? So the wave is reflected by in a moving vehicle, isn't it? So this acts as a source, right? So there will be a shift in the frequency of the reflected wave, isn't it? So from the frequency shift, the speed of the vehicle, any vehicle, can be calculated, right? And it is also helpful in tracking a satellite. So the frequency of the radio waves that is emitted by the satellite decreases when it moves away from the earth, right? So with the change in the frequency, then it can be calculated. The next one is the radar. Radar is the radio detection and arranging, right? So now here what happens, this radio waves are sent and it will reflect back, which is detected by the receiver which is present in the radar station. So from the change in the frequency, the speed, location, or the point where it is located of anything like aeroplanes, aircrafts, anything can be tracked. So tracking purpose it is used. The next one is the sonar. We have already dealt, isn't it? Ships sends the signal, isn't it, and it is received back after meeting an obstacle, right? So using this, the speed of the marine animals or the submarines, if any present, can also be detected. That is called a sonar, sound, navigation and ranging. So these are the applications of the Doppler effect. So with this we come to the end of the lesson, children. So in the next session we'll be dealing with the in-text questions and the book back questions, that is the numerical problems, in the next video. Now so far in this lesson we have learned sound as in longitudinal waves. We have seen the difference between the sound waves and the light waves, how to calculate the velocity of the sound, that is both the particle velocity and the wave velocity, factors affecting the velocity of the sound, and we saw about the reflection of the sound, especially the reflection at the boundary of the denser medium, the reflection at the boundary of a rarer medium, the reflection of the sound in plane and curved surfaces. Then we have dealt with the echo, applications of echo, and the Doppler effect. Then we said that there are formulas, that is expressions for the apparent frequency due to the Doppler effect, and there were 8 cases, isn't it? And each had a different formula, isn't it? So in the next class we'll be dealing with the numerical problems, both the solved problems, that is the in-text questions, and also the book back solution. Now your homework for today is that in the long answer, here you have question number 2 and 3. So the answer for these two questions are given in the PDF. I have uploaded the PDF. So you can copy these two questions in your classwork under this lesson. So already I have said that the first question should be written along with the diagram. So you can refer the answers for the PDF. I have uploaded the PDF. Submit the classwork after writing all the questions for the lesson acoustics, and submit in the school office on Friday. We'll meet you in the next session and discuss about the numerical problems of this lesson. Thank you, children.